Okay, today for our lesson 2 for our polynomial functions unit, we're looking at graphs of polynomial functions. So this is actually going to be new to you. There's two parts to this lesson, part 1 and then part 2 that kind of is like a worksheet and puts all of the concepts together. Okay, what we're looking is being able to identify key characteristics of the graphs of different polynomial functions. Okay, again, first couple slides of this lesson probably is going to be like, what are you talking about, Miss Mitchell? But as we keep going through it, it is going to make more sense, okay? So if we look at the degree of a polynomial function, so remember our polynomial functions were things like 8x cubed plus 2x squared plus 4x plus 7, okay? So say that that is your polynomial function. The degree of the polynomial function, so you're looking for the highest degree, and it's usually stated first, okay, in an equation that's written correctly. So your degree here is 3, okay? So that is actually going to help us determine something we call the end behavior as x approaches positive infinity. That is written as x approaches positive infinity. It's just like a sideways 8, and as x approaches negative infinity would be like a negative, like sideways 8. Okay, so when you're doing that, it's going to make more sense. But looking at just the degree of an equation, no matter how complicated this equation looks, will help us determine what our end behavior of x. Our leading coefficient is the coefficient of the term that is used to determine the degree of a polynomial function. So your leading coefficient here would be 8 because we use the degree 3. Okay, it may be a positive or negative number. If it's a positive or negative, it's actually going to help us, okay? A polynomial function may be an odd degree, so an odd degree would be 3, 5, 1, 3, 5, 7, 9, etc., or even degree, so 2, 4, 6, 8, as you keep going, as shown in the chart, which will be on our next slide, okay? So all of these things, so the degree, if the degree is odd or even, and then our leading coefficient are our things that are really going to help us with determining. So you just need to understand degree is an exponent. Leading coefficient is that number that's out front of that x, that base x. Okay, so I would copy out this chart as much as you don't want to. It will really, really help you for completing your homework and understanding like what a polynomial function is and like its end behavior, what the sketch would look like, what domain and range are, and what's max and min values. Okay, so we're going to look at 4 different examples here. Okay, so once you have copied it out, so like stop this video, copy this out, exactly what you see, and then restart this video, and it'll make more sense. Okay, so if we're looking at an odd degree polynomial, let's look at those first. Okay, that means that your exponent is going to be odd. So your exponent is odd when it's 3, right? If you look at your leading coefficient here is positive, or your leading coefficient here is negative. Okay, so depending on if it's positive, negative, and if it's odd degree, that is going to change some things. Okay, so the best way to remember this is for your end behavior is your sketch here. But the best way to remember this is if A, or your leading coefficient, is positive, then you're going to go up at the end. Your graph is going to go up at the end. If negative, you're going to go down at the end. And I'll show you that in these graphs, okay? So let's look. If we have a positive leading coefficient of positive 2, what way does our graph point at the end on the right? It points up at the end. If it is negative, we have negative 2 here, our graph is going to point down at the end. And I'm saying the end or on the right, okay? The right of the graph. Okay, again, let's look at this. If you are positive, we're going to point up at the end. If you are negative, you're going to point down at the end. Okay, so kind of cool. That's for graphing, and it's going to be the same every single time. Okay, and that is going to actually help us with our end behavior. Okay, if you can visualize and do this graph. Okay, but don't get too worried about graphing it. We'll get way more into specifics of that. Okay, so when you're looking at end behavior of a positive odd degree polynomial, okay, you are going to have end behavior as x approaches negative infinity. So as x's are approaching negative infinity, which is down here and it continues to go off the screen, your y's are also going to approach negative infinity. And then as your x's approaches positive infinity, your y's are going to approach positive infinity as well. And that's based on your end behavior of this graph. Okay. For negative, if we looked at this, as x is approaching, does it do negative? Yeah, it's going to go negative infinity first. So as x is approaching negative infinity, your y's are approaching positive infinity, right? So x is approaching negative infinity. Your y's are approaching positive infinity. And as x is approaching positive infinity, your y's are approaching negative infinity. Okay. Here, as your x's are approaching negative infinity, next is your y's are approaching positive infinity. And as x's are approaching positive infinity, your y's are approaching positive infinity. Okay. Here, as x's are approaching negative infinity, your y's are approaching negative infinity. As x's are approaching positive infinity, your graph is going down, approaching negative infinity. Okay, you will get more used to this, but this is the kind of the same for every single one of these. Okay, again, here we're looking at even degree positive. Even is 4 or 2 or 6 or whatever, and then negative even degree. Okay, so with that being said, you're looking at if A is a leading coefficient, if it's positive, it's up at the end, or if it's negative, it's down at the end. Okay, but that is only for, that's for all of them. But then the way to know if it's an odd degree or an even degree graph, if it's odd degree, you're going to have opposite end behaviors. So because you have opposite, so because you know it is a positive, it's going to go up at the end, well then you are going to start pointing down. Because you know it's negative, you're going to go down at the end, you're going to start pointing up. But for even degree, you have the same end behaviors, meaning that you're both going to, sorry, my thing's not writing nicely, behave, short form, okay? Even degree, you know that you're both going to point up because it's positive, or both your end behaviors are going to point down because your leading coefficient is negative. Okay, so again, I'm going to say these things like 4,000 times throughout the next couple of lessons, and you'll get used to that. Okay, but these are kind of things that you're going to have to kind of memorize and remember for different odd degree versus even degree leading coefficients, positive or negative. Okay, if you look specifically at our sketch here, your domain is all your x's, right? That's why we went over that in that first lesson. So as your x's are approaching negative infinity and positive infinity, they're going to continue going on forever, so you have no restrictions on your x's. Same with here for your y's, so your range for your y's are going to continue going up and forever and going down forever. So you just have y as an element of the real number system here. However, for these ones, you will see that your y values can only go as low as whatever this value is here, and they can only go as high as your value is here. Okay, so it is actually that is going to be, y has to be greater than, because you're going above this line, or equal to a, so your positive coefficient, so this would be greater than or equal to 2. Okay, and then y is an element of a real number system, such a y has to be less than or equal to a, which is 2. Okay, so that is your restrictions on that, so that your a value is your leading coefficient. Okay, just write that out. My pen is not working nicely. So your leading coefficient. Hopefully you can read that. Okay. Then your maximum minimum value, max and min, you don't have one because these just continue going on and on forever. But you do here, so you have a minimum value here, and it would be 2 in this example because that's your A value, or your maximum would be 2 as well. Sorry, -2 here because your that is a maximum value. Okay. So consider the polynomial function. This is where you're going to start to practice and actually understand what this chart does, okay? So this chart is going to be very confusing, so please don't be overwhelmed right now. If you are like, Miss Mitchell, I don't know what you're talking about, this makes no sense, please don't be overwhelmed. We're going to do lots and lots and lots and lots of practice with understanding what all of this means, okay? So copy out this example. I know you don't want to copy out stuff. You're like, oh, I'll just listen to Miss Mitchell talk, okay? But copy out this example so you have lots of examples in your notes for when you're doing homework and studying, okay? So consider the polynomial function f at x equals x cubed plus 3x squared minus 4x plus 1, okay? It wants us to know if the polynomial function is an odd degree or an even degree polynomial. Justify your answer, okay? Then it wants us to say if the leading coefficient's positive or negative. Should be pretty easy to see that. Describe the end behavior of the graph of the polynomial function. Okay. State the domain and range of the polynomial function. So with that, it becomes easy for A and B. I hope that it's easy to just read an equation. But C and D is where you have to go back to that graph or understand what your graph is going to look like to be able to state end behavior and state your domain and range. Okay. So let's look at, is the polynomial function an odd degree or an even degree polynomial? Well, I told you to remember to look at the highest one. The highest one's usually at the beginning. So your degree is 3. Well, 3 is an odd degree. So the function is an odd degree. And your reasoning is because the degree of the polynomial is 3. Well, 3 is an odd number. Okay, so pretty simple there. Leading coefficient is the thing that's attached out front of that, whatever you used to determine if it was odd or even degree. So it is a 1. There's no negative in front of it, so it's going to be positive 1, okay? So because it is positive. So right now we're looking at an odd degree positive function, okay? Sorry. Describe the end behavior of the graph of the polynomial function. So before we move on, we could actually try to sketch this a little. So based on what I told you, so the polynomial function is an odd degree of polynomial 3, and the leading coefficient 1 is positive. So you know if it's positive, it's going to end positive on the right of your graph, okay? And then because it is an odd degree, you're going to have opposite end behaviors, okay? So because you have that, you're going to be able to draw your graph. It's going to have 2 humps, which I'll get into why it has those 2 like changes in the graph, okay? But you know, just based on what I told you, an odd degree is going to have opposite end behaviors, and because the leading coefficient's positive, we're going to finish going to finish at the end going up, okay? So based on that and knowing that, or if you're like, Ms. Mitchell, I don't understand graphing yet, that's fine. Go back to your chart, see what a odd degree positive leading coefficient looks like, and then what your domain and your range are. The end behaviors, okay? So because the polynomial function is an odd degree with the leading coefficients of positive, the end behavior of the graph will be as x approaches negative infinity. I'm just going to redraw that. As x approaches negative infinity, so over here, your y is approaching negative infinity as well. And as x approaches positive infinity, your y is approaching positive infinity as well. You have to write this out in a question that I ask you. What the end behavior is, you have to write as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. So just like that, okay? You have to write those out. Okay, and then this last one, domain and range. So again, go back to your chart if you want to, but you should be able to look at this and say, well, X's and Y's are going to continue going on forever, so there are no restrictions. So your graph is going to be, your domain is going to be X is an element of real number system, range is Y is an element of the real. So this is the actual graph of that if you used Desmos. Okay, so that's from Desmos. That's the actual graph of that. Like obviously mine doesn't look identical to that, which is fine. Okay, so because of that like it doesn't matter what your graph looks like, they still are going to give you the same end behavior, same domain and range, etc. Okay, and this is what helps you with your end behavior because you know it's positive. It's going to go up at the end. And because you know it's an odd degree, you have opposite end behavior, so it's going to go down. Okay, again, we're going to get into lots of examples of this. Okay, so for this example, it wants you to consider each of the following graphs. We're going to state the sign of the leading coefficient, state our domain and range, and describe the end behavior. Okay, so for this, stating the sign of the leading coefficient. So, oh no, there's no equation this time. That's okay. Okay, that's fine. I've given you some hints for this. Okay, what way does our graph end? It ends on the right-hand side of the graph. It ends going down. So because it ends going down, I told you that it is going to be negative, okay, because we end down. Okay, so it wants you to state your domain and your range. So just look at your domain. So your x's, as your x's go up here, as your x's go down here, if they're going to continue going down and down and down, kind of like following the graph here. Okay, so they're going to go on forever. Same with your x's as they go up. Same with your range. So your y's are going to continue doing the same thing. So your domain is X is an element of the real number, range is Y is an element of the real number. Again, those don't change for these graphs for the most part, okay? Only if you have the same end behavior for those even degree functions. Describing our end behavior, so again, as X approaches negative infinity, Y's are approaching positive infinity. As X is approaching positive infinity, Y's are approaching negative infinity, okay? So they're the opposite, well, kind of opposite there. So think of X is approaching negative, well, your Y's are going up, so Y is approaching positive infinity. As your X's are approaching positive infinity, your range is going down, it's pulling your graph down, so your Y is approaching negative infinity. Okay, so another example of what you could be asked for from this stuff, and you'll get more and more used to it as we keep going. Use the degree and the sign of the leading coefficient to describe the end behavior of each of the following polynomial functions. So we're going to go and do an example here. And then there's another example on the next slide as well. Okay, so use the degree and the sign of the leading coefficient. So what is your degree? Your degree is 4. Okay, the sign of your leading coefficient is positive. So remember, when I said that, doesn't really matter, but you're going to use the degree and the sign. So your degree is 4. So if you know your degree is 4, you know each of your points are going to go the same way. So your end behavior is going to go the same. So it's going to be both up because we have a positive. Since it's positive, we know it ends at the top. And since it's an even degree, we know they're both going to go up. So it's going to be like 1, 2, 3, and then it's going to go up. That's a terrible graph, but there it gives you an idea. Okay, so it wants you to describe the end behavior. So think of this. So as X approaches negative infinity, as x approaches negative infinity, so we're going this way with our x's, negative infinity, our y's are approaching positive infinity. As x is approaching positive infinity, y's are approaching positive infinity. So that's how you would describe, so negative infinity to positive infinity, positive infinity, positive infinity for your end behavior. Okay, so again, you could just go back to my chart at the beginning and use that chart. But if you always have to reference that chart and you're not understanding truly what is your understanding of polynomial functions then, okay? So you're going to try to use that degree and the leading coefficient, draw it out, picture what it could look like, and then you're going to have your end behavior and know what your end behavior is, okay? Another example, each of the graphs represents a polynomial function of degree 1, 2, 3, or 4. Determine the least possible degree of the function corresponding to the graph and justify your answer. Okay, so a little bit trickier because we're determining the actual degree, but it's not impossible. Okay, so if we have a degree 1, what would a degree 1 look like? It would be a line. Is this a line? No. Okay, what if we had a degree 2? That would be a quadratic. Do we have a quadratic? Do we have a parabola? Nope. So it can't be a degree of 2. Okay, so those are pretty easy to eliminate. Now let's look at degree 3 or 4. Well, for degree 3, we know that it either has to look like this or it's going to have to look like this, depending on our end behavior. We know degree 4, we know either has to be both pointing up or it would have to be both pointing down. Okay, the only way to draw both pointing up, the graph would have to look like this, or both pointing down would be like this. So you actually know that it is going to be a degree 3 based on your end behavior having 1 point up and 1 point down, because I told you at the very beginning, any odd degree, you have opposite end behaviors. Okay, then we're going to determine the least possible function corresponding to the graph, which is 3. Okay, so just there, as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity, and the graph has 3 x-intercept. Again, we'll get into that. That's kind of another thing that helps us determine what our degree is, but because it passes through that graph a maximum of 3 times, that's the highest that that's the highest degree that our graph or our function can be. Okay, so what I'm going to get you to do is, there is homework now for this lesson, but I would prefer if you didn't do this homework yet and you actually do part 2 of this lesson video first with the handout, having me describe all of that, and you'll get more, like I go through like 10 examples at least in this next part 2 of the lesson. So wait to do this homework until you complete part 2, and then you're going to have a bunch of homework to do all at once.